Welcome to Chapter 5, the final chapter of Introduction to Quantum Computing. Chapters 3 and 4 described ideal circuits and algorithms that quietly assume the qubits stay perfectly coherent. Real devices do not behave that way, and the gap between them is exactly what this chapter is about. We define the NISQ era, compare the main hardware platforms, look at where noise comes from and how error correction proposes to handle it, and then meet variational algorithms, which try to do useful work with shallow circuits. We finish with chemistry and materials, the most natural application, and an honest report on where things stand. In 2018, John Preskill named the present era NISQ, short for Noisy Intermediate Scale Quantum. Intermediate scale means the device holds enough qubits that simulating it classically becomes expensive, roughly tens to hundreds, but not so many that we can spend most of them on error correction. Noisy means every gate, every measurement, and simply waiting introduces errors, with no full error correction layer hiding them. The practical consequence is a hard budget. If one 2-qubit gate succeeds with probability 1 minus epsilon, a circuit of M such gate succeeds with roughly e to the minus m times epsilon, so the useful circuit depth is of order 1 over epsilon. Several physical platforms are being developed in parallel, and none of them is a clear winner yet. This comparison stays deliberately qualitative because published device specifications change from month to month. Superconducting circuits give very fast gates and borrow fabrication from the semiconductor industry, but need millikelvin temperatures and usually couple only neighboring qubits. Trapped ions offer long coherence, high fidelity, and all-to-all connectivity, but slower gates and hard scaling. Photons barely decohere, yet they barely interact, so 2-qubit gates are difficult and loss dominates. Neutral atoms give reconfigurable arrays, with atom loss and still maturing fidelities. Connectivity matters more than beginners expect, because every inserted swap costs depth. Errors come from several directions. Decoherence is the loss of quantum information to the environment, and 2 timescales describe it. T1 is energy relaxation, the qubit decaying from the 1 state toward the 0 state, like an excited atom emitting a photon. T2 is dephasing, where the relative phase inside a superposition drifts randomly, destroying the interference that Chapter 2 showed to be the source of quantum advantage. Gate errors are imperfections in the control pulses, and measurement errors misreport a 0 as a 1. Notice the asymmetry with classical bits. A small voltage drift is simply rounded away, but a small qubit error never disappears and accumulates. Error correction refuses to store information in a single qubit. One logical qubit is encoded across many physical qubits, and we repeatedly perform syndrome measurements, which reveal whether an error occurred and where, without ever revealing the encoded state. Measuring the state would collapse it. Measuring only the error pattern leaves the superposition intact. The surface code is the most studied near-term scheme, with checks between neighboring qubits on a 2-dimensional lattice and a forgiving threshold near the 1% level. The price is steep. Figures on the order of 1,000 physical qubits per logical qubit are commonly quoted. Treat that as an order of magnitude, not a specification. If deep circuits are unaffordable, can shallow ones still do something valuable? Variational algorithms are the leading answer. The variational quantum eigensolver targets the ground state energy of a Hamiltonian, and it rests on the variational principle. The expected energy of any trial state is greater than or equal to the true ground energy, so every trial gives an upper bound, and we can never overshoot below the truth. The loop has 4 steps. Prepare a trial state with a shallow parametrized circuit called the ansatz. Measure the energy term by term, update the angles with an ordinary classical optimizer, and repeat until the energy stops decreasing. Let us make the loop concrete with the smallest possible example, a single qubit. The Hamiltonian is 0.4 times z plus 0.3 times x, exactly the form a molecular Hamiltonian takes once it is mapped onto qubits, a weighted sum of Pauli operators. The ansatz is Ry of theta applied to the zero state. A coarse grid scan over 25 angles reaches -0.4964. Gradient descent with the parameter shift rule, which evaluates the same circuit at two shifted angles, then converges to -0.5, matching exact diagonalization to machine precision with overlap 1. What the toy hides is measurement noise, because a real device estimates each energy from a finite number of shots. And VQE is not a free lunch. Its accuracy is capped by how expressive the ansatz is. If the true ground state lies outside the family the circuit can reach, no optimizer will find it. Measuring many Pauli terms to chemical accuracy needs a very large number of circuit repetitions. The landscape can also suffer barren plateaus, where gradients vanish exponentially with system size. The same hybrid recipe applied to combinatorial optimization gives QAOA, whose advantage over good classical heuristics remains an open question. In the early 1980s, Richard Feynman pointed out that simulating a quantum system on a classical computer is hard for a structural reason. The data required grows exponentially with the number of interacting particles. His remedy was to build the simulator out of quantum mechanics too. That is why electronic structure is the most cited application, especially for strongly correlated systems such as transition metal complexes and bond breaking. The hydrogen molecule is the canonical demonstration, traced out as a potential energy curve, and small molecules have been run on several platforms. But be clear about what they show. They validate the method, not a computational advantage. Where does that leave us? The honest summary has 3 parts. The theory is sound. Quantum algorithms for simulating electronic structure exist, and their scaling advantage over exact classical methods for strongly correlated systems is well-founded. The hardware is not there yet. Chemically useful accuracy on classically intractable molecules is generally expected to require error correction and therefore logical qubits, and the overlap region is still empty. Problems that are simultaneously classically hard and quantum tractable today have not yet been convincingly demonstrated. So approach any claim by asking what the best classical method achieves on the same problem, run by someone trying to win. That completes Introduction to Quantum Computing. Chapter 1 asked why quantum computing matters. Chapter 2 built qubits, superposition, and entanglement. Chapter 3 assembled gates into circuits. Chapter 4 covered the flagship algorithms. And this chapter came down from idealized circuits to the machines that actually exist. You now have the vocabulary to read the literature, the linear algebra to follow the mathematics, and, just as importantly, the calibration to tell a real result from a press release. The hybrid pattern of an expensive evaluator inside a cheap optimizer will feel familiar if you work in materials informatics. For the full written articles, check the AI Terakoya knowledge base.